Okay, this is chapter 3 for ACE Chemistry AS level. Um, and basically, chapter 3 is all about the electrons and their properties and their just how they interact with the atoms and that make up their atoms' different properties. So the first section is basically the simple electronic structure of an atom. Comes from the Bohr model. So we know that electrons are in energy levels, and depending on what row they are, it depends on how many energy levels the electrons are located. Energies can move up and down when they get excited and they release light, like fireworks. Um, but this is a simple structure of showing the different energy levels around the nucleus. Just a quick review that the lower numbers are closer to the nucleus, starting with the first energy level, or first shell having 2 electrons, and then the second one can hold 8, third energy level can hold up to 18, and the fourth is up to 32. So for example, lithium would have a 2-1 structure because there's 2 in the first energy level, and then the last electron has to go to the second energy level. Neon would have a 2-8, they have a full outer electron. And chlorine would have a 2-8-7 because in the second and third energy levels it can hold up to 8. So after it holds 8, it goes to the third energy level, and then there's 7 more for chlorine. So you can see in this table that the atomic number has to equal the number of electrons in a neutral atom. So for example, boron has 5 electrons, so it has 5, sorry, it's broken up in 2 and 3, 2 in the first energy level and then 3 in the second. You can see where sodium is as 11. So after the second energy level is full, that one outer electron is now in the third energy level. You can also see the pattern between hydrogen, lithium, and sodium, that they both have one outer electron because they're in the same column. So this is a little checkup. Write the electron configuration for the atoms: sulfur, magnesium, fluorine, potassium, and carbon. So you just got to make sure you know how to count the number of electrons and fill in the outer or the shells for each energy level. So sulfur is a 286, magnesium is 282, fluorine is 27, potassium is 2881, and carbon is 24. Again, if you add up all those electrons, they should get the same number of protons on the periodic table because they are neutral atoms, so protons and electrons are going to be the same. Okay, ionization energy, a big topic for ACE chemistry. They love to ask questions about ionization energy, even in A level. So the ionization energy is the removal of 1 electron from each atom of 1 mole of atoms in the elements, and they have to be in the gaseous state. So the reason why they have to be in the gaseous state, because that's the most chaotic phase. So that's the easier part, so it's easier to remove that electron when it's excited. So it's always 1 electron at a time, and 1 mole of that atom in the gas phase. So for example, calcium, move 1 electron. You can see the reaction is CaG, even though calcium is a solid, it's a gas, and it is breaking apart 1 electron, so it becomes a +1 charge. And the amount of energy required to remove that 1 electron is 590 kilojoules per mole. It's always going to be endothermic, meaning it's always positive because you're putting energy in to remove that electron. If it removes a second electron, you have another equation, but it is Ca plus 1 in the gas phase, and it makes Ca2 plus with 1 electron leaving. And that energy is a little bit higher at 1150 kilojoules per mole. So the reason why it's higher is because the nucleon number, the protons, hasn't changed. So there's a stronger hold onto its electrons, so it requires more energy to pull apart. And it becomes Ca2+. If you remove a third electron, again, one electron at a time, it's Ca2+ gas yields Ca3+, and a removal 1 electron. Notice if you add the charges up, they are the same on both sides. 3 plus and 1 a negative gives you a 2 plus. So, do you think the energy is going to be greater or less than the second ionization energy? Pause, pause, pause. And you are correct if you said greater, and it's a lot greater. 4,900 kilojoules of energy. And the reason why it's a lot greater is because you are now in a different energy level. So you went from a 4 energy level to a 3. So the noble gas configuration for elements are always going to be the most stable. That means it takes more energy to pull that electron away. So looking at the ionization energies, you can see it goes from about 600 to 1100 to almost 5,000. And basically it's always going to increase as you remove more and more electrons. So you can see this table from your text. Every ionization energy is higher as you go across for each element. And there are some patterns that we'll talk about with that. So let's look at the difference between 1 and 2 and 2 and 3 for calcium. So again, it's 500 kilojoules was the difference or so, but from 2 and 3 you're looking at 3,500. So why such a huge difference between the two ionization energies? And the reason is because of the noble gas configuration. It's stable when it's Ca2+. So when you jump to a different energy level, that jump is going to basically, you're at a noble gas configuration, so it takes more and more energy to pull that electron away, because we all know noble gases are going to be the most stable. So once they're the most stable, it takes the most energy to remove that electron. Okay, so the closer you move the electrons from the nucleus, the more energy required to remove it. So that's why after the second energy level, or second removal electrons, the outer electrons go away, and you have a Ca2+ charge, and it's a noble gas configuration. So again, you can see calcium, you can see something similar to calcium, which is going to be like, beryllium. You can see beryllium's big jump is after the second energy level. It goes from 17 to 14,000, 1,700 to 14,000. And then if you look at boron, the biggest jump is between 3 and 4, because it takes 3 electrons to get to noble gas configuration. So the biggest jump is going to be between 3 and 4. And then so forth. Carbon is going to be after 4 electrons. You can see a big jump from 6,000 to 37,000. And nitrogen is 5 electrons because it goes from 9 to 53,000. So as a new electron is removed, what happens to the ionization energy? It is going to increase every time. That's because of the proton charge doesn't change, so the protons and the nucleus are going to grab hold of the electrons even stronger and cause the radius to shrink, and then it takes more and more energy to remove that electron. There's a huge jump between the successive ionization energies when it becomes a noble gas configuration. So for group 1, it's always 1 electron, group 2 is 2 electrons, and then so forth. So look at nitrogen. So for nitrogen, it has 5 electrons become noble gas. So you can see they're in the same shell. And then there's a big jump from from 5 to 6, and then 6 and 7 are in the same shell as well. That's why the jump isn't as big. So you have 5 outer electrons and 2 in the first row, first energy level. Alright, so homework question number 1, page 35, number 2, you're going to write the different equations for each ionization energy. First ionization energy for calcium, third for potassium, second for lithium, and the fifth for sulfur. So to write the ionization energies, you always have to have the previous atom. So if it's the first, it's going to be a neutral atom, but if it's the third, it's always going to be the +2 charge, and then so forth. Alright, factors that influence ionization energy. So size of nuclear charge. The more nuclear charge generally is going to cause a greater ionization energy because it's holding on to the protons more, and that's if you go across the row, okay, not down. Distance of the outer electrons from the nucleus is going to, if the further their electrons are out, there's a less pull from the nucleus, the protons. There's less pull, it takes less energy to remove that electron, so ionization energy decreases. And shielding is a big effect. So think of blocking the electron. So if there's something blocking the proton and electron exchange, it's like shielding from other electrons, then there's going to require less energy to remove that electron. So shielding is going to cause a decrease of ionization energy based on less attractive force from the nucleus. It's almost like a block. Okay, so here is an example of the removal of each electron of sodium. Notice in sodium there's a big jump after 1 because sodium is in the group 1. So once you move 1 electron, it's a noble gas configuration. So it's a big jump right there. And then it's just basically a very gradual increase because it's always going to increase in ionization energy. And there's 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then there's a big jump because after 8 electrons, you're back to a noble gas configuration. So if you're back to a noble gas configuration, it takes a big amount of energy to remove that next electron. We know it's sodium because it has 11 electrons total. And we know it's sodium also because it has a big jump after the first. So here is a graph of the number of electrons. So it's removing the furthest one away the most, and that's why it's the lowest energy, because it's the furthest away from the nucleus. And then there's a big jump because now you are in a second energy level. And you have a gradual increase because you're in the second energy level the whole time for 8 electrons. And then to remove that 8 from that circle, that energy level, you are back to another noble gas configuration because you jump to another energy level, and then you remove the next 2. And those are the hardest ones to remove because they are the closest to the nucleus. Alright, page 36, talking about boron. So why is there a large increase between the third and fourth energy level? So again, boron has 5 electrons total, and the first 3, well, the outer 3 are in the second energy level. So you remove 1, you're still in the second energy level. Remove 2, you're still in the second energy level. You remove 3, you are now end of the, there's no more in the second energy level. So now the fourth and fifth are in different energy levels. So that's going to take a bigger increase of ionization energy to remove that fourth electron. So you can see here, 1, 2, 3 in the outer row. So that means they get rid of that outer electron, and then it takes a big jump to remove the next 2 because they are different energy levels. So explain why these figures confirm the electronic structure is 2, 3. It's because you have to have 3 in the outer row, outer electron shell, and there's 2 in the outer one because that leaves you the 4th and 5th electrons. All right, worked out example, page 37, number 1. This is basically trying to figure out what group the periodic table, or what group is this element belong to. So how do you determine what group it belongs to? And it depends on the big jump. So you can see here there is a huge jump between 6 and 7. That means it took 6 electrons to remove the outer electron level, and that means it has to be in group 6. Because that 7th electron is now in a different energy level, and there's a lot more energy required to remove that electron compared to 6th electron. Alright, last question for this section, number 4 on page 37. You can go through that on page 37 if you want, but I'll read it anyway. There are 6 ionization energies of an element, and these are the first 6, not just 6. But the first one is about 1,000, then 2,300, 4,600, 6,200, and then there's a jump at 37,000, and then 47,000. So what group on the periodic table does this element belong to? And then explain your reasoning. And they are very picky on their reasoning, so you want to make sure we explain it very well with the correct vocabulary. Alright, so that is the end of the first part of chapter 3. If you have any questions, please don't hesitate to ask.